How are you all doing this morning?
Pretty dandy.
Well, actually, it's no longer morning. It's well into the afternoon. So before we get started on today's lecture, I would like to talk to you a little bit about exam number, exam number 2, I think, right? So for exam 2, it is scheduled for this upcoming Thursday according to the syllabus. So let's start with, is everyone aware of that?
Yes.
Yes.
Okay. So there have been a number of students who have expressed to me that through, because of previously scheduled vacations or conflicts with another class that they're taking this summer, that Thursday date doesn't really work for them. So what I'm going to do, the exam will still be available to be taken on Thursday as per the usual schedule, but I will also have a slot open for next Tuesday. So that would be Tuesday, the 27th of July. And anyone who wishes to take their exam immediately following our class will be allowed to do so on Tuesday with no questions asked. So if you feel like you want to use the weekend to study more or anything like that, you're absolutely free to do so. But I'm not making 8 different versions of the exam. I'm only going to make 5. So Tuesday, your only option will be from noon to 3 p.m. to take the test. Is that clear?
Understood.
All right, so with that taken care of, let's wrap up transient analysis today. So we are going to talk today about what's called the total response of first order circuits. So to this point, we have learned about what's called the natural response. Okay, and so the natural response is effectively how a circuit behaves when any external excitation is removed. So in all of the examples that we've worked to this point, we have effectively removed any voltage and current and or current source from influencing the behavior of either our RL or RC circuit. So the natural response, Yn of t, we have found to have the form Yn at 0 minus for all t less than 0 minus, and Yn at 0 plus e to the minus t over tau, where tau is the time constant that I introduced at the end of our last class for all t greater than 0 plus, where tau is equal to L over R for RL circuits, and tau is equal to R times C for RC circuits. Today, we are going to be talking about forced response. So forced response is how a circuit behaves when external excitation, or you might see it called a forcing function, is included. So an example of a forcing function acting on a first order circuit might be something like this. We have a voltage source. Let's call it a 10-volt source. Let's say that we have a 5-ohm resistor. And then we have a 10-ohm resistor connected in parallel with a 200 millihenry inductor, like so. Our forced response would be this DC inductor current, IL, okay? And so what that really means here is that the response, the inductor current IL would not exist if that DC voltage source were not connected to the circuit. So we are under the assumption here that that DC voltage source of 10 volts has been connected to this simple circuit for all time. So the forced response is really what's happening at DC steady state whenever a forcing function or a source is included, okay? So we've actually dealt with this by understanding how inductors and capacitors behave in DC circuits. The total response is simply, so we could call this IL, could be IL at t is equal to infinity, because it's valid for all points in time. And so our total response, y of t, is going to be simply the sum of the natural response and our forced response. So what this is going to let us do is now analyze circuits where we leave voltage and or current sources in, okay? So I'd like to take a look at an example problem. Let's say that we have some current, let's call it 2 amps. We have a 5-ohm resistor, like so. And then we have a switch, which is initially connected at point A but at t is equal to 0, gets connected to terminal B. Then we have some capacitor. Let's call it 100 microfarads. And I'm going to define my capacitor voltage VC as a function of time like so. Now I'm going to have a DC voltage source. Let's call this guy 12 volts. And then down here, I'm going to have a 20 ohm resistor. Okay. So this circuit is different than the ones that we have previously analyzed because that 12 volt source is always going to be connected to the capacitor in some way, shape, or form. So we no longer have just a simple natural response problem because the 12 volt source always stays in the circuit. So we might be taking away the influence of the 2 amp source, but that 12 volt forcing function will always be present. Okay. So how we would go about analyzing a circuit like this is extraordinarily similar to what we have been doing. There's only actually one extra step, okay? So our first step is going to be to analyze the circuit at t is equal to 0 minus. So there, nothing has changed whatsoever. So at t is equal to 0 minus, our switch is closed at position A, and we are at DC steady state. So our circuit is going to look like this. We have 2 amps in parallel with 5 ohms. We have our capacitor voltage VC at 0 minus, like so. Here is our 12 volt source. And because nothing is connected to terminal B, it's just a simple open circuit. And so this is what our circuit looks like at t is equal to 0 minus. Is everybody okay with this representation?
What about
Why is a 20 ohm resistor not included?
Because I forgot to draw it. Thank you. Fantastic question. I totally forgot to do it. So now with the 20 ohm resistor included, does this look correct?
Yeah.
Yeah.
Okay. So how would we go about analyzing this circuit to determine VC at 0 minus?
Would it not just be 12 volts?
It would not.
Oh, okay. Could you go ahead, could you do source transformation on that voltage source on the right that's in series with that 12 and 24 or 12 and 20? You could change that to a current source and then add up your currents and stuff like that, maybe.
So you couldn't add the currents together because they're not going to be in parallel. All right, so let's think about this effectively using nodal analysis. That to me is going to be the easiest way to look at this, but I would hesitate to even really call this nodal analysis at all. I'm going to choose this node right here as a reference. So what I would like you guys to do is tell me what the voltage drop over the 5 ohm resistor is.
$10.
10 volts. Exactly right. All 2 amps of the current being supplied by the source on the left has to flow down through that 5 ohm resistor. And using Ohm's law, we can see then that the voltage drop across the 5 ohm resistor is simply 10 volts. So another way to look at this would be this voltage here, VA, is exactly equal to 10 volts, right? If we were
Right.
looking at this guy from a nodal analysis perspective. So what is the voltage VB, the nodal voltage VB with respect to ground?
12 volts.
12 volts. Now, you're correct, but I want to make sure that you didn't, you're making an assumption here implicitly that only works for this particular circuit, right? So VB is the voltage with respect to ground, right? So between this terminal over here and this ground node over here. The reason why VB is 12 volts is because we know that the current flowing through the 20 ohm resistor has to be 0 amps because it's not part of a closed current carrying circuit. Okay. So just saying VB is 12 volts because it's connected to a 12 volt source is incorrect. We have to acknowledge that that nodal voltage is with respect to our ground node. And since there's no current flowing through the 20 ohm resistor, that's why it happens to be the same as the voltage being provided by that source on the right. So if we know nodal voltage VA and we know nodal voltage VB, I would argue that VC at 0 minus is simply VA minus VB, because we have the nodal voltage associated with the positive polarity terminal of VC minus the nodal voltage associated with the negative polarity terminal of VC. So that means VC is equal to 10 minus 12 is negative 2 volts. Is anyone confused by the circuit analysis that we have just done? All right. So our second step would be to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch has changed from being closed at position A to being closed at position B, which means our circuit should look something like this. So here's our 12 volt source. Here's our 20 ohm resistor. This bottom rail is technically connected. And I'm going to replace my capacitor with a voltage source. because I know that the voltage drop across my capacitor is fixed. It will have a value of -2 volts, positive polarity on the left, negative polarity on the right. So VC at 0 plus must be exactly equal to VC at 0 minus, because we know that the voltage drop across the capacitor cannot change abruptly. So this has to be -2 volts again. So in this case, because the only thing that I've identified that I'm looking for is the capacitor voltage, we don't actually have to analyze the circuit at all. But if I were looking for any different quantity, we would have to do this analysis where we substitute in a -2 volt source in place of the capacitor. So I'm going to go ahead and move along to step 3, and we're going to work some more examples where step 2 is actually necessary. So step 3 is going to be a new one, okay? We will now analyze the circuit at t is equal to infinity. So at t is equal to infinity, transient condition has decayed and the circuit is considered to be at DC steady state again. So what this means is that our switch is still closed at position B, right? So the left-hand side of our circuit is going to be exactly identical as to what we've just drawn. We have a 2 amp source connected in parallel to a 5 ohm resistor. Here's our switch that's closed at terminal B. Here's our 20 ohm resistor. Here's our 12 volt source. But since we're at DC steady state, our capacitor now looks like an open circuit again. So we'll have VC at infinity here that we're trying to solve for. So what should our value for VC at infinity be?
0 volts.
I disagree.
Would it be 12 volts?
That is closer, but still incorrect.
-12,
-12 volts. Why did you say that, Sarah?
because it goes into the negative end.
I actually don't like that response. I'm sorry. I know that I've used it plenty of times, but we've always been using that when we're dealing with some sort of current. And I would argue that there's no current flowing in the right-hand side of our circuit here. So with that in mind, so we know that this kind of mesh-like current here has to be 0 amps because it's not, there's no way that current can flow through our open circuit, that is the capacitor, right? So if we were to do Kirchhoff's voltage law around this loop, starting at the bottom left-hand corner and following this 0 currents around its loop, we would see that VC at infinity plus 12 volts plus 20 ohms times 0 amps is equal to 0, which gives us VC at infinity is exactly equal to negative 12 volts. Does that make sense?
Yes, sir.
All right. So we would now calculate our time constant tau and put our relevant info into our general equation. So for this particular circuit, since it's an RC circuit, tau is simply R times C. So that would be 20 ohms times 100 microfarads, I think. Yeah. Which I get to be, so let's see, 20 times 100 times 10 to the minus 6. 2 milliseconds, and tau to the minus 1 power would then be 500 per second. So in our generic equation, where we have y total, or y of t, I don't remember which way I wrote it, I think it was just y of t earlier, is yn plus our forced response yf. What that's going to look like is y at 0 minus for t less than 0. And right now, I'm going to say that it's y at 0 plus e to the minus t over tau plus y at infinity. So that's how we're adding our forced response in to get our total response. Now there is an error here that I am intentionally making, and we're going to talk about it in just a moment and how to correct it, okay? But from a purely mathematical perspective, what I'm doing here makes sense. So I just want to talk about the very small change that we have to make, okay? So if we put in our values, we know that we would have y at 0 minus, which was negative 2 volts for t less than 0. And then we would have negative 2 e to the minus 500t minus 12 volts for t greater than 0 plus, if we just put stuff into our equation directly. Does anybody see what the problem is?
Well, if you're analyzing that circuit, like using that negative 2 e to the negative 500t minus 12 volts, say you analyze that, say you plug in a 0 for your time, that wouldn't, because I worked a problem like this on the web work. And basically the equation like worked for both cases. Like if I plugged in a 0, I got my current at 0 at time t is equal to 0 minus.
Right.
I don't know. And in this case, if you plug in a 0, then that would be like negative 2 minus 12.
Right. So negative 2 minus 12. So it would be negative 2 volts at 0 minus and negative 14 volts at 0 plus. So our voltage drop across our capacitor winds up being discontinuous, which we know cannot occur. So the only change that we're going to make is right here. So let me scooch this guy over a little bit. E to the minus t over tau. This is going to look like y at 0 plus minus y at infinity. And the reason why we have to subtract y at infinity, so effectively we can't just put in our initial condition anymore, is because we have to force our capacitor voltage and in turn our inductor current to be a continuous signal, right? So if I have y at 0 minus y at infinity, that's -2 minus -12 gives me positive 10. So 10 e to the minus 500t. Now at t is equal to 0, the value of the capacitor voltage is -2 volts when we approach from the left and -2 volts when we approach from the right. So we're left with a continuous function. So this generic expression here, let me put a box around it. Is what we will use whenever there is a source left in the circuit, okay? Now, a question that I'm very frequently asked by students is, how do I tell whether or not to worry about bothering with that whole y at infinity thing, okay? Or effectively, what's the difference between a total response circuit and a natural response circuit, okay? So a total response circuit is any circuit where a source is left in for all time. A natural response circuit is when they're taken out. That being said, there is literally nothing wrong with using this equation that I boxed in red for everything, because the forced response, when we don't have any external sources in, just goes to 0. So we're just adding, and we're adding 0 to the end and subtracting 0 from our initial condition. So it makes no difference whatsoever. So we can actually use this guy right here. Dang it. For literally everything, all of our transient analysis problems from here on out, and still be perfectly safe. We're technically adding an extra step that is completely unimportant, because we'll see that everything settles to 0 when we don't have any sources in the circuit, but it shouldn't take you very long to realize that. So let's look at another example problem or two.
What okay, so on the web work, what does this cover? Like, is this homework 14 and 15? Because like I tried to do just
yeah, so I would say that this is relevant for 13, 14, and 15. So,
okay, because I was trying to do homework 14, and that question is the only question that I've got on there so far, because I had to get help from Dr. Reese, because he was like right here beside me when I was working on it, and he kind of helped me to it, and I didn't know what was going on, and now I kind of understand it a little better.
Yeah, so the web work is, I'm trying to remember how the web work is laid out. It's been a while since I've looked at it. I want to say that homework set number 15 is really just ugly looking total response problems. So there are circuits that will require you to do the DC analysis of at t is equal to 0 minus t is equal to 0 plus and t is equal to infinity as needed will just involve like nodal and mesh, because the circuits are kind of large and ugly. But let me pull up web work real quick. Actually, I'll pull it up on this computer so that we can all look at it. Gotta find my cursor. Make things easier. You guys can see my Chrome screen.
Yes, sir.
Okay. So let's look at homework 13 specifically here. So this circuit would be an example of a natural response circuit because when that switch opens up, the 2 amp source no longer influences the 4 Henry inductor at all. Let's look at problem. So this guy, obviously the voltage source is getting taken out. In this guy, the current source is being short circuited, so all of the current being supplied by the current source will flow through that branch labeled with I2, and so the current source no longer influences the behavior of the inductor. So it's natural response. This guy is natural response because the voltage source is getting taken out. This guy is natural response because the voltage source is getting taken out. This guy is natural response because the voltage source is getting taken out. So let's look at homework 14 real quick.
Dr. Hartman, so
Yeah.
just looking at this, I've done homework 13. So I'm assuming that after learning what we just did today so far, that whether or not you need to include the infinity term is whether if the switch closes or opens and still includes a source of some kind is what we're considered to use the infinity.
That's absolutely correct.
Okay.
Absolutely right. So if we look at problem 1 here, let's look at this guy. So in this problem, how about we work this problem as an example? It's got multiple sources in there, so it stands to reason that, all right, so let's talk about the purpose of this switch in this particular case. So that 2 amp source on the left, it's always connected to the inductor, right? What that switch does is cause the 3 amp source to also start contributing to the behavior of the inductor as well. But since that 2 amp source never goes away, this is a total response problem. And we'll actually work it in just a minute. I want to look at a couple of the other ones here. Similarly, the 100 volt source here on the left is in no way, shape, or form connected to the switch. So the 100 volt source is always influencing the behavior of this inductor on the right-hand side. So this is also a total response problem. This is a, let's see, I'm trying to think about this. So this one, we're given the inductor current at 2.2 amps. We know the value of the inductor, we know the value of the resistor, so this is just simple natural response. But then at a later time, we add another, we open up a switch or something like that, and the time constant changes because we have 2 resistors in there. So this is actually a natural response problem. It's just 2 natural response circuits piggybacked on each other. There's no sources or anything like that to worry about. This guy right here is a natural response problem because the voltage source is being removed from the circuit. And this guy right here is a total response problem because the 10 volt source is always connected. So when that switch is closed, the 10 volt source is still influencing thing. When that switch opens up, the 30 volt source starts influencing stuff. So I want to work homework problem number 1 and homework problem number 5 from this set as examples. And then I think that'll probably be good enough for us. So let's see. All right, so we have a 2 amp source like so. And then down here, we have a 3 amp source connected in parallel with a 50 ohm resistor, if my memory serves me correctly. We have a switch, which is closing at t is equal to 0. Then over here, we have a 20 ohm resistor. And then over here, we have an inductor whose value is 0.1 Henry.
That's a 5 ohm, not a 50 ohm resistor, by the way.
Oh, thank you. All right, so this is our circuit. Step one, again, we analyze at t is equal to 0 minus. So in this case, at t is equal to 0 minus, our switch is open. So what we're left with is this guy. We have our 2 amp source, 3 amp source in parallel with our 5 ohm resistor. Here is our 20 ohm resistor. Since we're at DC steady state at t is equal to 0 minus, our inductor is going to look like a short circuit, and I need to flip back to that web page and see what exactly it is we're looking for. IL for t less than 0 and IL of t for t greater than 0. All right. So we're looking only for the inductor current here. Sorry. IL of t. Just for the sake of argument, I want to look for the voltage drop over this 20 ohm resistor too. So here would be IL at 0 minus, here would be VR at 0 minus. So how could we solve for either of these quantities? Anybody have any suggestions?
Would IL at 0 minus just be 2 amps?
2 amps, exactly right. So all 2 amps from that leftmost source will flow through the short circuit that is representing the inductance. So what's going on with the resistor voltage then?
It's gonna be 0 volts because no currents will go down that path. And from Ohm's law, V equals IR, we're gonna end up getting 0 volts.
Absolutely correct. All right, now we would analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is going to close. So our 2 amp source is still our 2 amp source, but now we have a short circuit which connects our 3 amp source and our 5 ohm resistor to the circuit. here is our 20 ohm resistor. Here is our voltage VR at 0 plus. And we are going to replace our inductor with a current source. And our current source will have a value of our inductor current. So it'll be whatever IL at 0 plus is, which has to be the same at IL at 0 minus. So that was 2 amps. So it'll be 2 amps. And it has to have the same direction as our inductor current. So that's why I've drawn it with direction down. All right. How would we figure out what VR at 0 plus is?
Wouldn't the current still go through the, okay, I wanted to say through the shot, but that's not a shot anymore. That's a current source. So
Right. So the
Would it
inductor
just be
current of 2
40?
amps is flowing down through that rightmost branch, but now we have other things to take into account. I'm sorry for interrupting you. Go ahead.
I was just saying, would it be 40 because those 40 volts? No.
So it'll be 40 volts if there is 2 amps of current flowing through the 20 ohm resistor. So my question to you is, how do you know the current that flows through the 20 ohm resistor? How did you determine that?
There be 3 amps flowing through the 20 ohm resistor. Because you have the 2 amps going up, the 3 amps going up, and then, well, maybe not.
So you're the closest to understanding what's going on here. I'm going to redraw this circuit very slightly, okay? So this is my 2 amp source on the left. Nothing wild or crazy there. This is my 3 amp source, and they're in parallel, right? My 5 ohms resistor is in parallel. My 20 ohm resistor is in parallel. And then my 2 amp source direction down also in parallel. There's only 2 nodes in our original circuit. And the voltage that I'm looking for this guy right here. So
Can we use current division between the 5 ohm and the 20 ohm and add the rest of the currents together?
we can do that, but it's a little bit of overkill. So you're mentioning that we can combine the currents together is very, very useful, right? So if we have 2 amps up and 2 amps down and they're in parallel, those guys exactly cancel each other out, right? So I could say that this guy doesn't do anything. And similarly, this guy right here isn't contributing either, right? The 2 amps up and the 2 amps down cancel each other out because that's how current sources combined. We learned that, I think, way back in like lecture 4. So the suggestion here was to do current division, find out how much current is flowing through the 20 ohm resistor, and then use that value. There is nothing wrong with that suggestion whatsoever, but I think it's a little bit easier to just multiply 3 amps times the equivalent resistance, 5 in parallel with 20, because we know that since everything is in parallel, they're all going to have the same voltage. So why make it take 2 steps when we can do it in 1? So I argue that VR at 0 plus is 3 amps times 5 ohms times 20 ohms over 5 ohms plus 20 ohms. Which, so let's see, so that's 3 times 100 over 25, so 3 times 4 is 12 volts. Is everyone okay with that analysis? We can absolutely do the current source method, but we'll find that we're obviously going to get the exact same answer just in 2 steps. So that would be 0.6 amps. 0.6 times 20 is 12. So it doesn't matter which way we do it. We're going to get 12 volts either way. Any questions about the circuit analysis here at t is equal to 0 plus?
Would you say being able to redraw the circuits like right above there when you connected the 5 ohm resistor to the top node and shared it with the 20 ohm resistor and the remaining currents, would you say being able to do that is the most important step when solving this problem?
Redrawing it, not necessarily, but recognizing that that everything is in parallel, yes. Which we don't have to redraw it to recognize that at all, right? If you identify your nodes, which I'm always a big fan of doing. So there's one node. There's my second node. If there's only 2 nodes in the circuit and everything is shared between those 2 nodes, it should be pretty obvious that everything is in parallel. I redrew it because it's probably a little bit easier for you guys to analyze looking at simple kind of window pane looking things. But once you recognize that everything is in parallel so that you can combine current sources, the analysis to me feels fairly straightforward. So
Thank you.
no problem. Yeah. So I would argue that recognizing that everything is in parallel is more key than redrawing the circuit. Yeah. All right. Any other questions regarding our analysis at t is equal to 0 plus? All right, so now we analyze our circuit at t is equal to infinity. So our 2 amp source sitting happily over here. Here's our 3 amp source. Here's our 5 ohm resistor. Here is our 20 ohm source, or excuse me, 20 ohm resistor, excuse me. Here is VR at infinity. And again, t is equal to infinity represents a DC steady state condition. So we replace our inductor with a short circuit. And so here is the inductor current, IL at infinity, that we're looking for. So who can tell me what either of these values should be?
Would IL at infinity just be equal to 5 amps?
5 amps, right, because the 2 amps and the 3 amps will combine together and a total of 5 amps will flow through the short circuit. Since all of the current is flowing through the inductor, obviously none of it will branch off and flow through the resistor. And so we should see that VR at infinity is 0 volts. So step 4, is everybody okay with that analysis before we move on, actually?
Yes, sir.
All right, so step 4, calculate tau and plug stuff in. So we calculate tau. So this is an RL circuit. Our time constant is going to be L over R. L is easy because there's only one inductor. So it pretty much has to be that, right? Our resistance is a little bit tricky because we need to pay attention to what we're doing here, right? So we're determining the resistance during the transient condition by looking into the terminals of a dead network. So our dead network representation means that our current source, both of our current sources are turned off. So that's where my 2 amp current source was supposed to be. Since we're during the transient condition, my switch is closed. Here's where the 3 amp current source should have been. Then I have my 5 ohm resistor. Over here, I have my 20 ohm resistor. And since I'm looking for the equivalent resistance or Thevenin resistance from the perspective of the inductor, I take the inductor out of the circuit and look in through the open circuit terminals left where the inductor used to be. So what should my Thevenin resistance be?
4 ohms.
4 ohms. So 20 in parallel with 5, so that's 100 over 25. Absolutely correct. So our time constant tau is 0.1 over 4 or 25 milliseconds. Tau to the -1 is then 40, so that's just simply R over L per second. And so our inductor current as a function of time will be, so what was IL at 0 minus?
2 amps.
What was IL at 0 plus?
2 amps.
What was IL at infinity?
5 amps.
E to the minus t over tau is going to be e to the minus 40t plus IL at infinity. We already know that was 5 amps. Where these guys together just look like -3. So we could say more easily then that we would have 2 amps for t less than 0 minus and -3 e to the minus 40t plus 5 amps for t greater than 0 plus. For our resistor voltage, VR of t is going to be 0 volts for t less than 0 minus. Then it shot up to 12 volts, e to the minus 40t volts, e greater than 0 plus, because we know that the voltage settled to 0 at t is equal to infinity. So it's going to look like 12 minus 0, e to the minus 40t plus 0. So the inductor here has a total response, looking response, because those current sources being added wound up forcing it to have a specific DC value at t is equal to infinity. But from the perspective of the resistor, it actually looked like a natural response problem because of how the inductor behaves, okay? So that's why I'm saying it's never gonna hurt anything to treat every problem like it's a total response problem, because you're just gonna wind up adding and subtracting 0 effectively from it. So did the analysis that we did in this problem, how did that feel to you guys?
I definitely understand it better now, like from the first time I worked on this problem.
Yeah, well, I mean, that's very reasonable because you didn't know what the heck you were supposed to do when sources were left in. So that's a very understandable conundrum you were in there. All right, let's look at that homework problem number 5 then. And all right, so we have a -volt source like so. We have a switch up here. I don't remember if it's opening or closing. It appears to be opening. At t is equal to 0. We have 4 ohm resistor, actually. Then we have a voltage source minus plus 30 volts like so, I believe. Yeah, negative polarity on left, positive polarity on the right. Then we have a 1 ohm resistor. Then we have another inductor, and it is 1/2 of a Henry. And we're trying to figure out what IL of t is here. And I'm not going to make this problem any harder than the homework problem, so we'll just worry about the inductor current. All right, so at t is equal to 0 minus, that switch is closed, right? So we're going to have something that looks like this. Here is our 1 ohm resistor. Here is our inductor current IL at 0 minus. Anybody care to tell me what IL at 0 minus is going to be here? Any thoughts?
Would that would that 4 ohm and 30 volt, would that be shorted out? So would it just be the current flowing through that 1 ohm resistor?
So it is the current flowing through the 1 ohm resistor, and you are correct that the 30 volt source in series with the 4 ohm resistor are shorted out. So I repeat my question. What is IL at 0 minus?
10 amps.
10 amps, yeah. 10 volts divided by 1 ohm is just 10 amps. Absolutely right. Our second step here would be to analyze the circuit at t is equal to 0 plus, but I'm not going to bother to do it. The reason why is I know that IL at 0 plus is exactly equal to IL at 0 minus is 10 amps. So redrawing the circuit in this particular instant, because we're only concerned about the inductor current, doesn't give us any new information whatsoever. So that's why I'm effectively skipping step 2. Does that make sense to you guys?
Yes, sir.
Yes.
All right, step 3. Our switch opens up. And so what we are left with is the 10 volt source, 4 ohms, 30 volts, 1 ohm, and our inductor is being replaced by a short circuit because we are at DC steady state again. So here is IL at infinity. So, any thoughts?
Like KVL?
Okay, KVL seems reasonable here. So we would have negative 10 volts plus 4 ohms times IL at infinity, because that's the only current flowing in our circuit, minus 30 volts plus 1 ohm times IL at infinity is equal to 0. Let me see what's going on here in chat. Can't we combine the, so there are no current sources, but you're absolutely correct, Mr. Abgar. Another way to do this would be to combine the voltage sources and then combine the resistors and use Ohm's law. So when we do KVL like this, we're going to see that 40 volts is equal to 5 ohms times IL at infinity, giving us IL at infinity is equal to 8 amps. The suggestion from the chat was to say that we combine the voltage sources together. So 10 plus 30, because they have the same polarity. Combine the resistors together. 4 plus 1 is 5. And we can easily see then that this is going to be 40 over 5 or 8 amps. Either way works. Personally, I would go the combining sources and combining resistances route, but the Kirchhoff's voltage law method there doesn't really take that much longer. It's a simple single loop circuit, so I understand why you would want to use Kirchhoff's voltage law, because I think I told you guys whenever you have a single loop circuit, use KVL. So that seems reasonable to me. So from here, we would need to figure out what our time constant is. Anybody have any idea what our equivalent resistance is going to look like?
5 ohms?
5 ohms,
Right.
probably.
So tau is going to be 0.1 Henry, I think. No, half of a Henry. I apologize. So 0.5 over 5 is 0.1. Tau to the minus 1 is then 10 per second. And so IL as a function of time here will be, let's see, what did we have? 10 amps. For t less than 0 minus, and 2e to the minus 10t plus 8 amps for t greater than 0 plus. That 2 came from y at 0 plus, which was 10, minus y at infinity, which was 8. So 10 minus 8 is 2. So how are you guys feeling about this total response stuff?
A lot better.
Okay. Do you want me to work further example problems, or do you guys feel like you're catching what I'm?
I mean, which I've already tried the homework, so I kind of knew what to expect. But I mean, I understand it like pretty well now.
Anybody else?
I think I'm picking up what you're putting down. Just need to practice it.
All right. So that textbook that I gave you guys, we talked about on the very first day of class, the free one or whatever, Circuit Analysis and Design by Ulabi, Maharbaz, and First. I think it has some pretty good example problems that you could look at. And I want to say some of the answers might be in the back. Honestly, in this case, this is one of the few cases where the homework is actually very representative of what you might find on the exam, just because there's really only a certain number of ways that I can do it. We analyze these circuits in the exact same way. The 3 practice tests that I have uploaded also all have, I feel, to be very representative examples of what you might see on your upcoming test. Yeah, if you guys want to do some practice on your own and then ask me questions during tomorrow's review session, that's perfectly reasonable. I'm also happy to stay on for another half hour or whatever and answer questions. Whatever you want me to do, I will do it.
Can you take a look at homework 15, number 2?
Sure. So did I already used all 12 pages. Let me edit document. All right, giving myself another page. Homework 15. Excuse me. Problem number 2. All right. So this is what I was talking about these. Homework 15 is the exact same thing that we've been doing. They are just really ugly looking circuits in general, but we can absolutely work this guy. So give me a minute to draw this monster. Sorry, so this one is 4. This one is 12. The switch is closing. Eight 24. All right. So one thing that I'd like to point out on this particular problem is that we are not explicitly asked to find our capacitor voltage, but we are going to have to find it at t is equal to 0 minus at a minimum to proceed with this. So I'll explain that in a minute. So I'm going to put VC of t here, positive polarity on top, negative polarity on bottom. Actually, I'm going to do it in a different color to try to indicate that it's not required by the problem, but that it is important. All right, so this circuit has a whole heck of a bunch of sources in it, and several of them are going to remain in after our switch closes. So this is definitely a total response problem. So at t is equal to 0 minus, our switch is open. Let me make sure I drew everything correctly here. Yeah, I did. Okay. So at t is equal to 0 minus, our switch is open. So I have to redraw this ginormous ugly thing again. Our capacitor is going to look like an open circuit. So here's VC at 0 minus. Then we have 12 ohm resistor goes there. .36 ohm resistor goes here. .3 amp source in parallel with a 16 volt source. There's our 12 ohm resistor through which our current IX at 0 minus is flowing. An ohm resistor. And then with, this is an 8-volt source in series with a 24 ohm resistor. And then over here, we have 12 ohm resistor. Okay. So the DC analysis involved in this problem is much more difficult than any of the problems that we've worked transient analysis on to this point, but this is just a DC circuit, right? So this is really just an ugly looking circuit that we could have solved several weeks ago. Since this guy is so big, do we want to solve it using nodal analysis or mesh analysis?
Mesh.
Mesh, okay. So I'm going to call this guy right here mesh 1. This guy right here mesh 2. And I want to be clear here. Mesh 2 is including this loop and this guy over here to the right. And the reason why is because there's an open circuit in the middle of it. Okay, so that's actually just one mesh. Let's call this guy right here mesh 3. This guy right here mesh 4. This guy right here mesh 5. So we have an interior current source because of course we do. So that means we're going to have to do super mesh. So our super mesh is going to be this guy that I'm drawing in purple. Like so. So let's write our KVL at super mesh 2, 3 equation first. So starting at the bottom left-hand corner, I see my 12 ohm resistor and a mesh current of I2 is flowing through it. Then I see the negative polarity terminal of my 4-volt source. Then I see my 36 ohm resistor and a mesh current of I2 is flowing through it. Then I see the positive polarity terminal of my 16-volt source, and that closes my loop. So any questions regarding this Kirchhoff's voltage law for super mesh 2 and 3 equation? All right. While I'm thinking about my super mesh, I want to go ahead and do my current relationship. So that would be that 3 amps is equal to I2 minus I3. We all on board with that?
Yes, sir.
All right. Now I will do my Kirchhoff's voltage law equations for my non-super meshes. So that'll be KVL at mesh 1. So if I start from the bottom left-hand corner, I have 9 ohms times I1. Minus 12 volts plus 4 volts is equal to 0. So we could actually solve that guy for I1 right now if we wanted to. Then I'm going to have mesh 4. So let's see, negative 16 volts. Then I have 12 ohms carrying a current of I4. Then 10 ohms carrying a current of I4 plus 8 volts plus 24 ohms carrying a current of I4 minus I5. And this is equal to 0. And I have to add another page. Where did it go? There we go. And I will next have KVL at mesh 5. And so let's see, it's going to be 24 I5 minus I4. Minus 8 plus 12 ohms times I5 is equal to 0. And I'm not in the mood to get out MathCAD and all that kind of stuff and solve this guy, so I'll just assume that you guys can solve this system of equations. How would we relate that current IX to our mesh currents?
It would be negative I4.
So IX at 0 minus would be negative I4. I absolutely agree with that. How would we find VC at 0 minus?
Nodal analysis.
So if we're going to do mesh, we shouldn't do mesh and nodal. We should be able to relate VC to our mesh currents as well. So let's talk about how I might do that real quick. I can say pretty easily that no current is flowing through my 4 ohm resistor. Does everybody agree with that?
Yes, sir.
All right. So the positive polarity terminal of my capacitor voltage can be thought of as this node up here. Does that seem reasonable?
Yes.
All right. So what I'm going to say then is VC is the voltage drop over the 4 volt source minus this 12 ohm resistor on the left times I2. I'm saying it's the 4 volt drop plus this voltage V12, where I know that I2 is flowing into the negative polarity terminal, which is where that negative sign comes from. I could just as easily say that it is going to be 36 ohms times I2 plus 16 volts. Either way is going to give me the exact same answer. So do you guys see how and or why I did that?
Can you explain it again?
Sure. So what I'm doing is I'm just writing Kirchhoff's voltage law loops, right? So let me erase this guy and this purple jibber jabber as well. Okay. So for that 4 volt minus 12 ohms times I2, I'm just writing a Kirchhoff's voltage law loop around this guy that I'm doing in orange. And for the second representation, I'm just going around this loop that I've drawn in light purple. I could actually do it for any loop I wanted to once I know the mesh current. So if I were feeling, I don't know, particularly squirrely for whatever reason, I could write one around this loop as well. But the two that the one that I did in orange and the one that I did in light purple are the ones that are going to have the least number of terms. And so to me, they're the least, the ones that I'm least likely to make a mistake on writing. So with the orange loop, I'm following that loop counterclockwise. And so since I know that there is no voltage drop over the 4 ohm resistor, I don't include it. Then I see the positive polarity terminal of the 4 volt source. Then I see my 12 ohm resistor through which a current of negative I2 is flowing. For the light purple loop, again, the first thing I see is my 4 ohm resistor, but it's carrying no current whatsoever. Then I see my 36 ohm resistor, which is carrying a current of I2. And then I'm jumping over that current source because I know that I can't tell what the voltage drop over a current source is, except that in this case, there's a voltage source directly in parallel with it. Then I see the top polarity, or the positive polarity terminal of my 16 volt source, and then I'm back down at the bottom, which is my negative polarity terminal for VC. So that's just two simple Kirchhoff's voltage law loops that we could write to determine VC, and then based on our known mesh currents. All right, so the next thing we would do is analyze a circuit at t is equal to 0 plus, and I'm going to be a little bit lazy here and copy and paste some stuff. Let's see, select all this junk. Paste all this junk. So what changes when my switch closes, right? When my switch closes, I have a short circuit between these 2 points. And so now I'm going to have some mesh current I6 that I have to take into account as well. And my capacitor is going to be replaced by a voltage source, having a voltage of VC at 0 minus, which gives me an eighth mesh I have to worry about. So I would just write all my equations for this. So do you guys want me to walk you through that as well?
I think I can get it.
Yeah. Then at t is equal to, so let me copy this real quick. Do I have enough room left on the page? It looks like I do. Great. Edit, paste. At t is equal to infinity, my capacitor is now an open circuit again. So I will have plus minus VC at infinity, which gets rid of this mesh 8. So mesh 2 is doing this noise again. And then we would analyze all of those and figure out what Ix is. So after t is equal to 0 minus, we don't actually need to know what VC is anymore. So for our analysis at t is equal to 0 plus, how does Ix at 0 plus relate to our mesh currents?
Would that be I6 minus I4, looks like?
Absolutely correct. And Ix, sorry, lowercase, Ix at infinity is also going to be mesh current I6 minus mesh current I4. So I'm really not a big fan of homework set number 15 here because I feel like these problems are just hard for the sake of being hard. And they're not even hard. They're tedious for the sake of being tedious. They don't teach you anything new that we didn't learn doing the stuff that was covered by homeworks 13 and 14. So I am inclined to just drop the grade for homework number 15. I mean, it's reasonable practice, I guess, but it's just, I feel that this is better practice for nodal and mesh analysis than it is actually for transient analysis. So yeah, it wouldn't hurt my feelings at all if you just completely skipped homework set 15 because I think that these problems are pretty much pointless.
Don't worry, it would not hurt my feelings either.
Yeah, I mean, again, they're just big and ugly, but give you no new information or anything like that. They're just ugly for the sake of being ugly. So one day I will learn to program in Perl and create my own homework sets, and future students will never have to look at these terrifying things again. Anyway. Any other questions regarding any of these homeworks or transient analysis or literally anything? We got a review session for tomorrow's class period. So, you know, if you don't have anything now, think of something before then and we'll spend 2 hours covering whatever it is that you want to talk about.
So if we're choosing to take the test on Tuesday, obviously we don't have class Thursday because of the test. So our review is that Tuesday, like tomorrow?
Yes, the
As well?
review
Okay.
for everyone is tomorrow's class period.
Okay. Thank you.
Any other questions? All right. Well, I will see you guys tomorrow at 10 a.m. I hope you have a great rest of your day.
See ya.
I have a question.
Yes, sir.
There are no op amps on the practice exams that you put up. Could you put up a few practice problems that will be similar to what will be on the exam for op amps?
Absolutely. I will work on compiling that tonight, and I apologize for not having done so before now. So
It's-
yes, I will
it's
100%
okay.
do that.
Thank you, Professor.
Mhm.
Have a good day.
All right, you too.